So I will talk about flux creeping strong ping theory. That's our last two students. Martin finished PhD, 2 years ago, and Filippa is working now on another project. So strong ping theory actually goes back to Labush and Larkin-Ovchinnikov, so end of 60s, 70s. So it's, the oldest theory of pinning, even though it was a bit forgotten. And every time I try to remind what it is about, it simplifies complicated problem of statistical averaging over disorder with relatively simple averaging of over one pinning center. So one assume low density of defects, then displacement of vortex is proportional to the force. So this is equation which describe it, and this is non-linear equation, so it's not so easy to solve. And one can look at it in the following way, that interaction of a given vortex with all other corresponds to effective parabola potential, where C is effective elasticity. And when we move vortex lattice through disorder through the pin, then this parabola is moving, and this is the pinning potential. And here is kind of video which is not working on this computer, so you cannot see what actually will happen. But the jump, you'll have profile that vortex goes here, and then it's jump to the next branch, goes here, jump to the next branch, and so on. So this is kind of view both in all three dimensions. So here, when you have this curved line, that's Z direction as a X direction, and away from the pin, it's relatively vortex little bit curved. Then when it comes, it jumps to the defect, and it gets this kind of tip of vortex which sits on the defect. We move it stronger, but the tip considered to sit on the defect, and eventually here is jump back to unpinned state. Now, if we change it and now view this axis not as Z along the vortex, but Y in the transverse direction, we go to the transverse problem. So if there is head-on collision, vortex goes straight on defect, then that's as I presented. Now, if it comes at some transverse distance, then it comes to this point and then jump here and go and jump here. But kind of it's come with some non-zero impact parameter. But if impact parameter is a bit larger, then it never approaches to the state where the jump occur, and there is a smooth motion, and this type of motion doesn't contribute to the average pinning force. So as a result, we have effective trapping area, which is colored blue and red, and this defines transverse trapping distance. So the result of all that, which again goes back to Labush and Larkin-Ovchinnikov, is that the average force, we should average the force. Force is derivative of potential, and we have jumps here, and these jumps produce the contribution. If there were no jump, the average would be zero, and as a result, we have the pinning force is given by the sum of these jumps in the energy landscape. Now we can calculate IV. So now all was old work of other people. Now what we try to do is calculate the IV curve or force velocity curve, and that's what kind of was common belief that how IV curve, the critical force, and the should bends here and so on. Now, if you do calculate it for the strong pinning in this model, then you get completely different curve. That's our work with Alex Thoman. That you get that the pinning force is actually independent on velocity, and what we have is shifted flux flow. This is flux flow. Now you add pinning force to it, and you get shifted flux flow. So this is actually equivalent to what in tribology, the science of friction, is called Coulomb law of friction, which is that kinetic friction, so friction of sliding object, okay, is equal to the rest friction. So that's what we learn at school, and actually never thinking why it's the case. So in our situation, we can derive this Coulomb law, and we can look on experiments, and this is old classic textbook data by Kim and co-authors. Actually, this is the paper experimental, well, it's difficult to say verification, or this is 64, Bardeen-Stephen was 64, so either Bardeen-Stephen explain data of Kim, or Kim confirm theory of Bardeen-Stephen, so they are kind of the same year, and that's flux flow, and that's with the pinning you see it's just the same shifted flux flow, and the essence of the paper was that this slope is proportional to magnetic field, but what we see here is shifted flux flow and a little bit curvature here that actually I will come in a moment. So now if you look on the effect of creep, then in the standard collective pinning there is not much life above critical current and not much effect of creep. If we have strong pinning, as I said, pinning exists way above critical current, and so creep also will modify it and shift, will reduce pinning force, and we will have shifted curves which actually remind pretty much the curvature here. So we cannot say maybe it's also effect of creep, maybe not. It's all data we don't have hand on them. So then we try to, okay, so how to describe first this creep in the strong pinning theory. And if temperature is 0, then there are these two branches, and transition between branches comes at the end point. So boom, jump here, then goes to another branch, comes to the next end point, jump, and so on. Now, if it's non-zero temperature, then vortex can jump before the end point. It just goes over the barrier, and here it goes over the barrier, and a result of it, well, that's how it kind of moves. We should calculate the probability of this jump to jump from one branch to another, and backwards jump. They have different barriers. We should add them and write kinetic equation. And as a result of it, branch occupation change. The jump shift from here to here. So that's where the branch happens. We can find the position of the jump simply by equating barrier to t log velocity. And from here we know the jump happens. If velocity is slow, then it happens, if velocity is large, then it happens close to the end point. If velocity is slow, then vortex has time to try many times to jump over the barrier, and eventually the jump happens here. knowing the jump, we can find the value of the jump in energy. From the value of the jump in energy, we'll calculate average force, and we get current voltage curve. So for low enough temperature, creep is rather weak, and everything happens close to the end point of the branch. Near to the end point, we can do Taylor expansion, and the barrier grows as the distance in the power 3/2. Well, that's usual Landau type of expansion there. And so as a result, we get effective barrier, which behaves as a difference from critical current at the power 3/2. Not 1 as like in Anderson creep, but 3/2. And close to equilibrium, so at very low velocity, this jump shifts to the crossing point. Then we should really look how the distribution function is changed, is different from the step function, and then we obtain linear IV curve, so that's the linear IV curve here, with the slope which exponentially depends on the barrier and temperature. That's what was called thermally assisted flux flow, and the old experiment on high TC, that resistivity close to transition line, so at higher field, that's IPCO, actually has exponential dependence, which were never really understood. Well, here we provide some explanation. So that's also theoretical curve, how should creep evolve from zero temperature with increase of temperature. So this linear slope, which I was talking before, so this linear slope is not visible here. Well, here there are numbers for this linear slope, so depending on the temperature is like 10 minus 15 to 10 minus 3, so at the highest temperature. So the most effect that you see with the creep is the shift of the flux flow to lower temperature and appearance of curvature. That you have finite slope, you really have to zoom very strongly, so it's much weaker effect. And then as you see, this curve looks pretty much similar to this curve data of Kim and co-authors, and we try to compare it with more recent experiments. And here we have two datas, one from Evandre group on niobium diselenide, and here more recent of Pratap Raichadori on amorphous moly germanium film. And dots are experiments, lines are theory, and you know, these curves are not parabolas, so we're not trying to fit something to straight line or parabola. It's rather complicated. It looks complicated. On a formula, it's also is complicated. And I would say I was very surprised to see how good one can fit the data. Well, the editor looks like also was surprised. They gave some editor suggestion. I don't know what it is, but people tell that it's good when you have such a mark. Now, how actually you do this fit, it's not a completely trivial thing. So that's original data for different temperature. And here you see two effects. One is simply shift of everything to the left, which has nothing to do with creep. It's just because critical current depends on temperature, as all like through Ginzburg-Landau thing. And then you have appearance of curvature. So how to disentangle these two effects? And the idea is, well, what are these two effects? One is simply that everything depends on temperature. Close to TC, critical field goes to zero, meaning energy goes to zero, critical current goes to zero. So you have simple effect of that, and it has nothing to do with creep or anything. And another thing is really effect of creep, that vortices can jump from one potential well to another, and how to separate them. So the idea was that you take original data, then you fit straight lines, this blue straight line, so to linear IV curve, which what would be without creep, and you extract parameters, well, the value of critical current, which is just extrapolation of this curve to zero, and the slope. So that's the first step. After you got this slopes and critical current, you rescale the data, putting them, measure them as a function of current you put to the critical. So you shift all these curves to the same straight line there. And now on this plot, all that what you see is effect of creep, because you scale away kind of Ginzburg-Landau dependence. Well, Ginzburg-Landau I tell from theory. We have experiments, so we don't use any kind of fit into the theory. We just feed data, we rescale the data such to separate one temperature dependence from another, and that's kind of we get this fit, and that's how we generate. So, and we not only get this fit, we can extract parameter like how critical current depends on field, how barriers depends on field, and all of them, I don't have time to show these details, but all of them looks reasonably agreement with prediction of strong, so like this field dependence of critical current and so on. All this looks in agreement with theory. Now, Campbell length. Well, what is Campbell length? Campbell length is due to Archie Campbell. So Archie Campbell passed away about 2 years ago. Well, that's obituary. That's his wife wrote in Guardian. So he is famous for Campbell technique. Actually, I learned about Campbell much before that I learned about Campbell length. At the time when I studied superconductivity, there was such a book. Sorry for not English translation. It's Campbell-Leavitt's Critical Current in Superconductors. Nowadays, not so many people, well, young people learn it from something else. But at my time, well, this book was translated to Russian. I could get it in Chernogolovka, and that's what I studied to learn about pinning. So, well, that's here at some of the conference. So what is Campbell length? It's the same as London penetration depth, and it's measured in such a case. You apply small AC field. The difference is that you already have large DC field, so you try to push a little bit field when there are already vortices present. So it reminds the thing in the public transport. Don't do it at Corona time. You try to push people in the bus, and it's very hard because people inside are pinned, and people inside actually don't even notice that something is getting pushed from outside. So the force decays exponentially. So how to describe it? So Archie Campbell suggested to have the spinning force and say that every vortex is pinned and sits at the bottom of potential well, and we replace this force by the curvature, by parabola, and this alpha is the curvature, and this gives this curvature. Well, this gives first solution, which exponentially decays at the length which is related, is inversely proportional to square root of this curvature. So if the curvature is very large, then it costs you so much to displace the first vortex and field doesn't penetrate. If the curvature is zero, then all the vortices goes down. So That's a bit simplistic approach. If you try to do better, then you need actually to average over different vortices and different defects, because some vortex sits at the bottom of potential, but other may sit at the place where curvature is maximal or another. So we have to perform this averaging over curvature, and as a result, we obtain that the average curvature is given by the jump, not in energy, but the jump in force. Average force is the integral of derivative of potential and is given by the jump in energy. Average curvature is derivative of force and is given by the jump in force. So we have, now if we study creep, then it's very simple. From the value of barrier, we know where new jump in occupation will happen. For calculating average pinning force, we look on the jump in energy. For the value of calculating curvature of Campbell length, we look on the jump in force. And that's the result. So here, for different strengths of the pinning potential, marginally pinned, so almost no pinning, and very strong pinning, green line is current, measured current. So in magnetization measurement, that's what you would call critical current induced by creep. It goes from 1 to 0. So on this axis, it goes to 1. Here, everything relaxes to 0. And this on the top is Campbell curvature. It doesn't change that much. It goes from 1 up to 20% or down to 20%. It's on the left axis, what is the scale. And there are two remarkable features. One is that current decreases, and that's natural due to pinning current decreases, due to creep current decreases. That's what we call effect of creep, that everything relaxes towards equilibrium where there is no pinning. But Campbell curvature actually first grows and only later goes down. So curvature grows, which tells you that it looks like pinning gets stronger because your potential becomes more and more sharp at the bottom. So how come that happens? And another strange feature is that above so-called reversibility line, when current already decayed to 0, nothing actually happens to Campbell curvature, and it's not much different from that without relaxation, like plus minus 15% or 20% up and down. So how do we understand?
2 minutes, please.
Yep. So trapping. So why curvature goes up? It's mostly because trapping length goes up, because those vortices that come at the distance can jump here and get to creep. And well, that's one can do some calculation all that, and if you write formula, you can get even reasonable analytic fit here. And why Campbell curvature is non-zero above reversibility line? Simply because we have, going from one branch to another, we always should take lowest branch, but there is cusp, because it's this branch cross each other, and so there is jump in derivative, and this jump gives equilibrium Campbell length. And this is in agreement with experiment. So for Ruslan Prozorov, this is how current decays, and this is how Campbell length also goes down. Here it's negative, which means that the curvature grows. And as you see in that's the reversibility line above which there is no measured current, and about which Campbell length is the same wherever you go up and down. But you see, nothing happens with Campbell length here. It's about the same as at lowest temperature. And another remarkable feature of the data is that in the field-cooled state, not in the bin state, but the field-cooled state, there is no relaxation whatsoever. Nothing. There is no creep. And, well, I will stop here. I have slides which describes why we also do not expect to have creep in the field cooled, but that's since we are over time, let's stop here. Thank you for attention.
Thank you very much.